And thanks very much to the organizers for inviting me here. So everything I talk about is going to be joint work with Manjul Bhargava and Jerry Wang. So it's a real pleasure to be here, celebrating Professor Lenstra's life and work. And I want to begin by discussing one of the conjectures. So here's a conjecture, and it is in a paper by Ash, Drakenhoff, and Zabari, and it's due to Professor Lenstra. And here's what it says. So fix a degree. So fix an integer n greater than or equal to 2. So when monic polynomials f of x with integer coefficients of degree n are ordered by the size of their coefficients, the density of elements such that the ring Zx mod g of x. So given a monic polynomial, you can construct this ring, very natural rank n ring to take. So the density of polynomials such that this associated ring is a maximal order. It should be the ring of integers in a number field. This density is 1 divided by zeta 2. And this is a particularly beautiful conjecture because this density doesn't depend on n. Very nice indeed. So I should state that it's very hard even to prove that there are infinitely many such polynomials for each degree that exist, and that they exist is the result of Kiran Kedlaya. So he proved that for each n, there exist infinitely many and in fact, there exist infinitely many polynomials of degree n such that Zx mod f of x not only is a maximal order, but in fact is a maximal order in an Fn number field. This conjecture is still open, but I'll state a related result. We saw from Ashwin's talk that there are many natural ways in which you can order polynomials. So this conjecture is stated for the ordering corresponding to, when you order polynomials by the size of the coefficients, but if you order them by the size of their roots, then it becomes an easier problem. And in joint work with Manjul and Jerry, we prove that the modified conjecture is true and the modification is that instead of ordering polynomials by the size of the coefficients, we order them by the size of their roots. But today I don't want to talk about this problem. I want to talk about a related problem. I want to talk about what happens if instead of restricting to monic polynomials, you also allow the leading coefficient to vary. So today we will be considering the very analogous story of binary n-ic forms. If you allow the leading coefficient to vary, you may as well homogenize the polynomial. And so we will be considering the space of binary n-ic forms. So for the ring R, let n of R be the set of homogeneous degree n polynomials with coefficients in R. Now, just like you can construct a ring from a monic polynomial, you can also construct a ring from a binary n-ic form. Nakagawa gave a recipe. So given an element f of x comma y in Vn of z, Nakagawa showed how you can associate to this binary n-ic form a ring that I'll call Rf. And in fact, Melanie proved that this is a very natural object, that this is simply the ring of integers. Sorry. That this is simply the ring of global sections of the scheme cut out by f in P1. Sorry, I should say, let's assume that the discriminant of f is non-zero. I think Nakagawa required that assumption to construct his ring, but this assumption was removed by Melanie. We will, of course, be interested in asymptotics, so discriminant zero forms are negligible and irreducible forms are negligible. So we can ignore all such subtleties. Yeah.
Maybe I should have asked this a few moments ago. So in general, right, you could this maximal order condition could be relaxed at finitely many primes. Should I generally assume that when you state a theorem that if I relax the maximal condition of finitely many primes, then I'm removing finitely many terms from an Euler product and the same statement is going to hold?
Exactly. Exactly. Absolutely.
Assume that.
Yes.
For the theorem, when you say size of the roots, is that like the maximum root or the product of the roots?
Maximum root. I beg your pardon? Some density. Yes, absolutely. The same 1 by zeta. You don't somehow expect, I mean, this density comes from the behavior of the p-adic places. So unless you do something really horrible with your ordering, you expect the density to remain constant.
One other question we'll pause here. Do we know or at least expect that if you do take polynomials instead of over Z over some ring of integers and some base number field, that something similar will be true?
Exactly. We would expect the density to just change from 1 over zeta 2 to 1 over zeta k of 2, where k is your base number field. That's not
proved.
Yes.
So just to clarify, in the original conjecture, the order is based on the maximum coefficient.
Absolutely. Okay. I will more precisely state the order for the binary n-ic forms just to absolutely. It's completely parallel. Okay. And so now you can ask the same question. How often is Rf the ring of integers of the number field? And so in fact, let me just settle the question of the order right away precisely. So we will have a height function. We will order these elements f of x comma y by a height function, and the height function is going to be function h, and I can just find it on the real numbers as well. Let's easiest. So height of a naught x to the n plus dot 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 plus a n y to the n is simply the maximum of the sizes of the AIs. Okay, so the result I want to talk about for today's talk is this joint work with Manjul Bhargava and Jerry Wang. And the result is that when integral binary, so here we have to fix n greater than or equal to 3, actually, not n greater than or equal to 2, but when n is greater than or equal to 3, and when we order integral binary n forms by height, we order them by height, then the density forms corresponding to maximal orders is 1 by zeta 2 times zeta 3. I should say that the n equals 3 result is due to Davenport and Hale-Brown. They didn't quite state it in this way. Instead of considering binary cubic forms ordered by height, they took G and Z orbits on binary cubic forms and ordered them by discriminant, but they proved this exact result. When n is 2, we get a different order factor. So let me make a couple of remarks. So first, I'll note that this is a slightly stronger version of the arithmetic Bertini theorem. For P1Z, as conjectured by Bjorn. Who in fact proved the arithmetic Bertini theorem conditional on the ABC conjecture and with a different ordering of the binary n forms question. So I say slightly stronger because to prove the arithmetic Bertini theorem, you'd only need to prove such a result as n is going to infinity, not for each n. And in fact, the arithmetic Bertini theorem could be true even if these Euler factors were these densities were different for all n, just as long as the limit as n goes to infinity turns out to be this, and it's quite a nice fact that for each n we get the same density after n equals 3. The second remark I want to talk about is the corollary of this result. It's going to be too surprising that you can use the fact that we are constructing that we can prove the existence of forms that correspond to maximal orders and number fields to prove that there are lots of number fields for some definition of lots. So what we can prove is we can show that the number of number fields with discriminant less than x is at least x to the half plus 1 by n minus 1. So we
Degree n. So
yes, sorry. Thank you.
Is this also with a symmetric group?
Yes, absolutely. All of them are going to have, or most of them are going to have symmetric group. We can't show the existence of any other Galois group.
Ask, does your method also apply the Bertini theorem for other curves over Z, or is it only for or higher or even higher dimensional varieties? My conjecture, or it's
This is all we can do. Okay. I mean, for example, if you want to think about P2Z, then you have to look at ternary forms, and there we can do ternary cubic forms, but not higher than that.
you do have some
Yeah, ternary cubic form, but ternary in lower degrees, there are often ad hoc methods that work out, and we don't have anything systematic. And this is a slight improvement on the previous x to the half plus 1 by n, which would be a consequence of the previous result that I stated. And this itself is just a slight improvement on x to the half plus 1 by n squared, which is due to Ellenberg and Venkatesh. When it comes to lower bounds, I should say that the best known currently is that this number is less than x to the big O of log n the whole squared due to a beautiful work of Len K. Oliver, Robert Hood's right here, and Frank Thorne. And the correct answer should be x if we believe Barley's picture. So there's a long way to go in both directions. Okay. So I now want to talk about the proof of this result. And that's what I'll spend the rest of my time doing. So as Kiran pointed out, this 1 by zeta 2 zeta 3. It's a product of local factors, and the way these local factors show up is from the local probabilities of being maximal. So of course, the ring is maximal. If it is maximal at every prime, and the condition of being maximal at a prime p, the condition of Rf being maximal at a prime p, is the mod p squared condition on the coefficients of the form. And so that's a probability we can actually compute, and that's the density we can actually compute quite easily. I shouldn't say quite easy. I mean, we use the work of Ash, Zabiri, and Brackenhoff to compute this density, the density for the monic case, and use that to compute the binary any case. But given they were this way, straightforward, and what we prove this is all, of course, I'm just talking about the proof of this result. Trying to work with multiplication. So the local computation says that the density, so again, n is always going to be greater than or equal to 3. The density of elements in V and Z such that Rf is maximal at P is as no doubt you have guessed, 1 minus 1 by p squared times 1 minus 1 by p cubed.
Is this maximal in some étale algebra or is it in a field?
Maximal in some étale algebra. So basically you can take, I mean, this construction of Kagawa's works just as well if you're doing it over ZP and okay. So what does this tell us? This tells us that the density. So let's start trying to compute the density of things that are maximal everywhere. You get quite a long way. The density of F such that Rf is a maximal order. This is going to be less than or equal to the density of F such that Rf is maximal at all primes less than or equal to some m, clearly. And once you can compute the density at one prime, you can compute the density at finitely many primes using the Chinese remainder theorem. So this is less than or equal to the product p less than or equal to m of 1 minus 1 by p squared times 1 minus 1 by p cubed. And so then now you can take limit as m goes to infinity and you can get one direction of the claim. So this entire density is less than or equal to 1 by zeta 2 times zeta 3. You get this just completely for free once you've done the local density computations. So the difficulty is in proving the other direction of the bound. And the reason the other direction is difficult, so let me just give you some heuristic way in which to think about this problem. I just want to point out that there are about x to the n plus 1, something growing to the order of x to the n plus 1, elements in V and Z with height less than or equal to x. So the discriminant of these elements go all the way up to x to the 2n minus 2 because the discriminant is a degree 2n minus 2 polynomial in the coefficients. Which means we have to worry about primes going all the way up to x to the n minus 1. That's a lot of primes. So these primes could rule out, like for all we know, you take primes 2, 3, all the way up to x to the n minus 1, and they just rule out every single one of these because each of them could rule out x squared elements, for example. Some of them rule out much more than x squared elements. Prime 2 will rule out something like x to the n plus 1 by 4 elements. So what's needed to prove the lower bound is a sort of tail estimate. We have to prove that even as these primes are getting larger, they're not ruling out too many forms to be maximum. And the reason that's kind of a difficult question is because that's the mod p squared condition. P squared is going all the way up to x to the 2n minus 2, and we are interested only in a box of size x inside that set. So, I mean, x is really tiny compared to p. So, sort of some of the traditional methods of equidistribution are not really going to do it for us here. So in order to prove a tail estimate, we're going to use just one fact about non-maximal rings. It's a very simple fact, which is that if Rf is non-maximal at P, then P squared divides the discriminant of F. And in fact, the third of the questions that Lillian talked about yesterday in her slide is exactly this this question. This is, we're trying to understand, in essence, how often a polynomial, namely the discriminant polynomial, takes on a square free value. And the input that's needed to do that is what's called a tail estimate. So let me state what the tail estimate is. Okay, so inside Vn of Z, let me define a set UP, and this is just going to be the set of all elements such that P squared divides their discriminants. Now, what do we expect to be true about the size of UP? Let's just heuristically think about this. So what I want to say is, what is the size of elements which belong both to UP and have height less than X? Well, what would we expect? We know how many elements there are with height less than X, X to the n plus 1. And we know that P squared dividing the discriminant should be like a probability 1 by P squared event. So perhaps we would guess that this is less than X to the n plus 1 by P squared. And in fact, if we could prove this, that would immediately imply the theorem. But such results are usually very hard and we don't come anywhere near proving this. So luckily, we don't need it in its full strength. We can weaken this in a few ways. The first way is that we don't need this for each individual prime, we only need it on average over prime. So all we need is summation P greater than M is less than X to the n plus 1. And we would expect this to be true, just from the previous heuristic. But we don't even need this. We just need M to the delta for any delta greater than 0. And in fact, we can even further weaken this. We can add a little O of X to the n plus 1 term here, and we're still fine. So we started off with what we expect to be true. We weakened it tremendously. We're left with something which is really weak in comparison, but this is going to be enough. A tail estimate of this form will immediately imply our main theorem, and it's not specific to our situation. This is a sort of standard sieve theory input. Yeah.
Is that little o uniform in M?
Yes.
Okay, that's
Absolutely. And right, so in fact, I mean, this is not specific to the situation of discriminant polynomials of binary n forms. If you have any polynomial, you're trying to show that it takes a lot of square free values, an input of this type is enough for proving that it takes on the correct number of square free values. Yes.
Can you even weaken it to replace the left-hand side by like the size of F in the union of all the UPs?
Yes.
Okay.
Yes. And I'm going to pretend that they're the same thing. That's a great point. That's a great point. So the point is that we're summing over F in UP, but an F can belong to multiple UPs. So do something about that. And you're right, the way I stated it, it's not ideal. So what I will do is I will, in addition, insist that the discriminant of F is not 0. And now the problem is much better because there are very, very few P's for which F can belong to a UP. Because as P squares start dividing the discriminant, that blows up pretty fast. And we don't really worry about 0 discriminant forms because they're negligible. We can ignore them in all our estimates. It's an excellent. And so this is our main technical result. This is what we actually do prove. And this immediately implies the main result. Okay. So before I proceed, I want to do this. I want to talk about. Yeah. So actually, let me do this now. So p squared. So UP is the set of all forms. So p squared divides the discriminant. But there are many ways in which p squared can divide the discriminant of a form. And some of those ways are easier to handle than others. That's going to lead us to the following definition. So we say that p squared strongly divides the discriminant of some element f in V and Z if p squared also divides the discriminant of f plus pg for all g in V and Z. So what I mean is, if I look at a form and I know that p squared divides the discriminant even when I reduce it mod p, then p squared divides the discriminant strongly. So for example, I have the form ax cubed plus px squared y plus pxy squared plus py cubed. Then no matter, then like just reducing mod p, you know that p squared divides the discriminant. It has a triple root mod. So these are the forms that we say p squared strongly divides the discriminant of. Otherwise, we say p squared weakly divides the discriminant. The prototypical example here is the form. Let me take x cubed plus x squared y plus pxy squared plus p squared y cubed. And here, if I just had a p and a p, then all I know is that it has a double root, and therefore p divides the discriminant. And the square, this p squared here, is crucial for p squared dividing the discriminant. So this is genuinely a mod p squared condition that you need for p squared to divide the discriminant, and so we say p squared weakly divides the discriminant.
So it should divide it at least.
Yes. So if p squared either weakly or strongly divides the discriminant, then p squared definitely divides the discriminant. So you can use this to partition UP into two subsets. We will partition UP into the ones where p squared divides the discriminant strongly and the ones where p squared divides the discriminant weakly. And what I want to say without providing any details or any details really is that there's a very general method which you can use to prove tail estimates for this set, strongly divisible by p squared. And this method again is not specific to the discriminant polynomial. If you have any polynomial and you break up the set of points where the polynomial is divisible by p squared into strongly and weakly divisible, then you can use the Ekadal-Sev and its refinements by Sarnak, Poonen, and Bhargava. So you can use this to prove the tail estimates for the strongly divisible elements. So if you replace UP with UPS, then the Ekadal cell is going to do it for you. And so all we need to do is prove this tail estimate for the weakly divisible ones. Okay. So there, unfortunately, general methods come to an end. For most polynomials, so here we are particularly concerned with the discriminant polynomial, but most polynomials, we don't know how to do a square free Sylphon. And the reason is we can't prove a tail estimate for the weakly divisible primes. In our situation, however, we have a very special polynomial. The discriminant polynomial is one that admits many symmetries. And what we're going to do is we're going to use those symmetries. So before I plunge into the proof in general, I want to give some intuition for the proof by very quickly sketching out the idea that Davenport and Heilbronn used to prove their version of the result for binary cubic forms. This is not quite going to be in the language in which they stated it, but it's essentially the same method. And I'll ask you to recall from Ashwin's talk that we have a group action on the set of binary forms coming from the group GL2, which acts via linear change of variables. So for binary cubic forms, we're going to use the action of this GL2. And this is due to Davenport Heilbronn. Again, I'm sweeping some details under the rug because their method really applies to GL2Z orbits on binary cubic forms when ordered by discriminant, but you can kind of go from ordering by discriminant to ordering by height with a few analytic tricks. So I'll just sketch out the proof. So what's the problem, right? Like we have an element in UP weakly divisible. And well, what that means is that it looks of this form. I said this is prototypical, and it really is. It looks exactly like this. Which is to say, it looks like this after a change of variables. So you can change variables. And I'll bring the p squared to the beginning. This gamma is an element in GL to Z. And then I'll change by the element that's not in GL to Z, but is in GL to Q. 1 by P1. And that takes it to A by Px cubed plus B by Px squared y plus C by Pxy squared plus dy cubed. Then I'll multiply by P to simply get ax cubed plus bx squared y plus cxy squared plus pdy cubed. I want to point out that doing this, you lose all control of the height because of the first transformation. You've brought a root mod p to infinity, and this root mod p can be huge because p is huge compared to x. So doing this doesn't allow you to retain any control whatsoever of the height. However, the discriminant goes down by a factor of p squared. And now I can use some further reduction theory to bring the points with these much smaller discriminants closer together, and you can count them. So this sparse set has been brought closer together via the action of GL2. I mean, like you really need quite a bit of the action. Like you use GL2Q to get here, but then you have to use GL2Z in order to bring all these points with smaller discriminant together. But you use this action to bring a very sparse set of points into a much smaller bound where you can count them using geometry of numbers. I also want to point out, though, without going into any detail, that another potential idea here is to take an action of a reductive group and move points which are weakly divisible by p squared to points which are strongly divisible by p squared, and then use the Ekadal sieve to bound them. That's another action. It works in certain cases. Here you don't need it.
Why did you use the gamma first? Couldn't you have just multiplied by like 1 over p and then gotten the p in front of the a coefficient instead of the d?
Oh, you're saying why did I put the p squared here instead of
Yeah, yeah. Why did you flip them?
Because in the general thing, we do this for like not serious. It's just a purely acidic choice.
Okay.
It's purely acidic choice, and just so that it sort of fits up with the notation of the paper later on.
I think it's not just flipping because he doesn't know a priori where the polynomial, where it is. So you have to move it wherever it is. You have to move it. You're asking whether you move it to 0 and infinity.
Right.
But the problem is to get it from something else to one of those. Where you need a big.
Absolutely. That's a very crucial point. This matrix is going to be very large because a priori the double root is at some random point in P1F.
Can the A, B, C, and D be divisible by? I'm guessing not C and D.
It's an excellent question. If C is divisible by P, then it's not going to be weakly divisible. It's already going to be strongly divisible.
What about the other ones?
A and B could be arbitrarily divisible by P. And you can get
C.
Just C. C has to be indivisible by P, and then you'll be weakly divisible and not strongly divisible. Okay. So now with this a little bit out of the way, let's move on to the odd n case, and I'm afraid I'll be somewhat brief. So the problem here with using GL2 is that GL2 is just not big enough. There isn't enough of GL2 to do this kind of thing. Even for n equal to 4, not enough GL2. So we want a bigger group. So let's assume that n is 2g plus 1, so it's odd. And so what we're going to do is we're going to take our weakly divisible points, we're going to lift them into a much bigger vector space, which admits a much bigger group action. And so let me tell you what that bigger space is. So this is a space that has been studied quite extensively in arithmetic statistics. And it is the space Wn, which is, so for all rings R, we'll let Wnr be the set of matrices, pair of symmetric matrices. So let me actually just write this as A comma B, where A and B are symmetric n cross n matrices with coefficients Aij and Bij elements of R. And you can think of them as quadratic forms as well. But this is not quite the representation that Ashwin was considering yesterday. I'm not insisting to be half integral. The integer valued quadratic forms if you're taking R equals Z. What are the integer coefficient? Matrix coefficient, I've forgotten the terminology. But it's a dual space to that. Nevertheless, the group SLNR acts on WNR. And the ring of invariants for this action is very easy to describe. So in particular, we have a map from WNR to V and R. And the map simply sends a pair A comma B to the determinant of AX minus BY. I'll call this map inv, which sends a pair to its invariant binary form. And the polynomial invariance, the ring of polynomial invariance for the action of SLNC on WNC is generated by the coefficients of the invariant form. And now, what we're going to do is lift our set. So what I want to do now is I want to take UPW and I want to construct a section. Say section, I mean when you take a form here, you map it here, you take the invariant form, you get back the same form. So here's the section. Given a form f of x comma y, I'll first move it using some gamma in GL2 z to something of the form p squared a naught x to the n plus p a1 x to the n minus 1 y plus dot 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 plus a n y to the n. And then I will lift this thing into a pair of matrices. Not particularly important what these matrices are, but the one important thing is there are a lot of zeros over here. So the first one starts with anti-diagonal. And it's 1 p a naught 1, and then there are some other numbers here. While the second one starts with ones on the off anti-diagonal, and then some sort of Pn R ones.
So how large are these matrices?
Absolutely. So these are n cross n matrices.
Then I cannot count. It looks as if the diagonal is twice as long. I don't understand.
Also, these are only even numbers.
These are all-
B1, C2 up to Cn, and here it's Bn minus 2 up to B1. Yes.
Maybe you're gonna, is this the element that corresponds to the canonical square root that you have
Ooh,
in this case? Of the,
of the known,
IN.
the ideal. These are in fact so n here is odd. So this just corresponds to the identity element.
this is the,
This is the identity element because it has the G cross G blocks of zeros.
okay.
So actually I want to talk about this. So so the arithmetic invariant theory of the space has been studied quite a bit. Oh, sorry, you seem like.
Well, but the, okay, well, I'll ask you later. We were just speaking a different language because the identity element doesn't square to the right thing, so.
Oh, then yes, absolutely. Sorry. I think of it as not the toss. I immediately. Yes, you're absolutely right. You're absolutely right. Yeah, so this is a very, very important point, actually. So let me then describe the invariant theory for the space a little bit, the arithmetic invariant theory for the space a little bit. So given an F in Vnz, what you can do is you can take inv inverse of F, and then you can take SL3Z orbits on this space, And you can say, well, what's this set correspond to? And it turns out that this set is related.
Where three is N. That's all.
Yes, SNN. Thank you. Is related by work of Wood to the class group, to the two torsion of the class group of RF. It's a cover of the group. But the thing is that it's not actually the two torsion of the class group, it's a tosser of this. When N is odd, this tosser is trivial. So you can just think of it as being essentially in bijection to something which looks very much like two torsion of the class group of RF. However, when N is even, it's not. This tosser can often be empty. And so in fact, you don't expect the map from WNZ to VNZ to be surjective. And so there is no lift that can be constructed. And that's the reason I'm considering odd N separately from even N. Odd N is much easier because.
You mean by, oh, you mean, when you talk about torsor, are you talking about some, by torsor, are you think of it as a group, are you think of the class group as a team and?
So what Melanie proves, and perhaps Melanie should say this afterwards, but I mean, but what she, so these correspond to triples I delta, where I squared is equal to a certain ideal class, where this is an ideal class inside RF. Now this turns out to be a square.
And is odd.
When N is odd. And so you always have an element. So this is in bijection with the two torsion. Something very close to the two torsion of the class group. When N is even, this might not be a square, in which case you're in trouble.
It's not even torsor. Torsors have to be non-empty. Sometimes if you're talking about a torsor,
Sorry, maybe I should say twist.
I don't know, but anyway, it's
Absolutely. So anyway, so the result is that these are actually in bijection with pairs I comma delta, such that I squared is contained in this times delta. Is that correct? And such that the norm of I is equal to the norm of delta squared times norm of IN minus 3. So that's the exact bijection. It pairs this up to equivalence, the usual equivalence, which is multiplied by something multiplied delta with the correct thing. And this is very, this is so this when N is odd, IN minus 3 is a square, in which case you get something that looks very much like the class group. And when N is even, then you can't do this. Okay. So yes, so these elements correspond to I squared being equal to IN minus 3. Sorry, so to I being the square root of the class of IN minus 3. If you can think of it as like an identity element of sorts. Moreover, this lift looks pretty good because there are only p's in here. There are no p squares. So it looks like it's strongly divisible by p squared. It looks like the discriminant. So because there's a map from Wn to Vn, Wn inherits the height, it inherits the discriminant. And it looks here because the discriminant of Wn is equal to the discriminant of the resolvent form, which is divisible by p squared. It looks very much like this is strongly divisible by p squared. That's misleading, because these zeros actually have to be zeros, not just zero more p's. So if you consider this lift as an element inside Wnz, it is not strongly, the discriminant is not strongly divisible by p squared, because you actually need these two blocks to be zeros. So what we will do is we will consider it as a member of the smaller space. So I will define W naught inside Wn to be the set of pairs A comma B such that Aij and Bij are 0 for all 1 less than or equal to Ij less than or equal to G. And it turns out that if I take the group G naught inside SLN, the biggest group inside SLN, which preserves W naught, that the invariant theory for G naught on W naught is much richer. So on W naught, the discriminant polynomial factors. And not only does it factor, there exists a polynomial Q such that Q squared divides the discriminant. And the reason P squared divides the discriminant of our lifts is because P divides Q. So what's really happening here is that for an element in our lift, we have Q is divisible, this Q invariant is divisible by the prime P. And now this is just wonderful because our previous condition involved points where P squared divides the discriminant for P greater than M. And now you can replace that condition with simply the Q invariant is bigger than M. And okay, instead of you're getting a bunch of composite numbers in there, but primes are very, very numerous among numbers. They're like, you're just losing a log X if you replace prime with every number. And we have that much room and to spare. And so that, doing this and then counting elements with large Q invariant and bounded height finishes the proof in the odd case. And in the remaining 1 minute, maybe, I'll talk about what needs to be done in the even case. Oh, this one? Oh, yes, yes. So when n is even, well, here what we do is the map Wn to Vn is not necessarily surjective. Is probably not surjective. We can't prove this, but it's probably not surjective. We certainly can't construct a lift. And we shouldn't expect to be able to. So instead, what we do is we take UP, weakly divisible, and I'll put a subscript n, just to indicate that we are looking at binary enic forms. And I'll map it to, so we have an even degree form. Let's make it an odd degree form, multiplying by y. And now you've got an odd degree form again. And this has a lift, which we just constructed. However, when we multiply it by y, the last coefficient has now become 0. So we are sitting inside, the image is sitting inside pairs A comma B, where the determinant of B is 0. So if we run this previous game, we're going to have to count only those B for which the determinant is 0. And we handle that by modifying a method of Eskin and Katznel's. So they count determinant zero symmetric matrices in homogeneously expanding domains. We have to count them in fundamental sets for these actions of groups, which are not at all homogeneously expanding, but extremely skewed. But we use their ideas, their methods to adapt it. And once we do that, we can count and say the same. And I'll stop now.